Right. How's everybody doing?
We're trying to survive this week, to be honest.
Survive.
Yes.
Is COVID really that bad?
Not just COVID,
Oh, are you talking
especially,
about schoolwork?
yeah, school, because this is like our submission for our first milestone for GAM. Yeah.
Okay. All right. I understand. Okay. The first thing is the midterm. Uh, the There is a Thursday, Deepavali. I think it's coming up very soon, and I was thinking the best way to kind of take care of it would be in the recess week, when hopefully everybody is just a little bit free. So um, I don't know. The plan was for you guys to be in the school to take the test. Uh, I don't know if it's possible, so we'll have to do it online. Okay. Now, this is the key thing. We have tested it with freshmen. Okay, 200 plus, and they all were able to log in into the quizzes. So you guys need to make sure you write down your login, your password on a piece of paper, and just type that. If you try to use your password manager in your browser, you're getting this denial of service, right? Because you try a couple of times with some vaguely remembered passwords, then it kicks you guys out, right? But if you actually know what the uh, actual information is, then you shouldn't have any trouble, right? So the denial of service is what's causing some of you not to get in and the others to get in. And when you get into the denial of service, the whole system slows down because almost a bunch of people kind of trying to provide incorrect passwords. I think the system sort of goes into some sort of a defensive mode, right? So if we have to do it in at home and you can't get in, then you have to come to school, right? And take it in the school. So it's probably best if you stay home and take it at home, right? It's open book and whatever, but you gotta make sure that you don't want to come to school because school obviously there'll be invigilators. It'll be a lot more strict. Okay, so I'll give you more information by Thursday about what we'll do on week 7. But I'm thinking of it as a makeup class for Thursday. So that way everybody can just get a holiday and no need to kind of do makeups. All right. So what is it that I want to talk about today? Yeah. I'm a little bit behind, but I'm still okay as long as we are learning stuff. I hope so. And today we want to finish off with this whole Mu semantics and kind of look at how we want to write our functions. How do we design them? Because we are adding sort of new information compared to HLP2. Okay, I have a presentation, and folks, make sure to get your attendance in, please. Right? Otherwise, you create work for me, and um, I don't like work, just like you guys. Who likes work? Okay. Uh, because normally I don't use PowerPoints, so I've been putting in some time to make these PowerPoints in class. I kind of, just use code to explain. But I think with the situation the way it is, I think some of you may prefer having some sort of a tighter, kind of like boundary, so you know what was covered. So, yeah, hang on. You're able to see my screen, right?
Yeah.
Okay, so what I'm going to do today is just sort of more or less complete the whole moving part, and this is quite important. Actually, it's the easy part, because when we get to templates, this whole move stuff is going to get a whole lot more complicated. And so it's best if everybody understands this material today a lot easier without templates. And I have some code that I'll write up uh, to kind of show you how we can author move base functions. Okay, but before we do anything, I think all of you probably need some sort of, how should I put it, some sort of little primer. So here's a quiz for you guys, right? You don't need to go online or anything. This is just a quiz right there in front of you. So some declarations and definitions in the first, in the top part. And then we end up with some questions. There are 8 functions, and I want you to kind of just think about it, and then we'll discuss whether these calls are valid or not. And obviously, these are the sorts of questions you will see in the midterm, right? Okay, we have a function called mutate. As you can see, it takes what I'll later on call an L value reference. And then we have the function observe that takes a const reference. 3 and 4 are kind of similar, but 3 returns a value and 4 returns a read-only value, right? This used to be popular before C++11, but not anymore, but I just thought I'll add that in too. And then we have a string object 1, which is just a L value. And don't worry if you are getting a little bit confused with this whole L value, R value, I have a big discussion, right? But 2 is obviously a const L value object. So then you see these 8 calls. Let's start with observe 1. What is your opinion about this function?
Oh, true, obviously.
Sorry? Observe will work?
True.
Okay. It works. You're absolutely right. So the string object is going to be the parameter S is going to get a reference. So there's no copies made, none of that stuff. And this is essentially what HLP2 was propagating, right? Hey, this is a good style of programming for what we call input parameters. Input parameters are parameters where observe, as the name implies, okay? Take some information from the string. It's not going to change anything. And it may actually generate new information that it's writing to a file, whatever. But it needs this purely as an input. And so no copies made. And this is hopefully how, generally speaking, you write your code. What about observe 2?
It works as well.
Sorry? I couldn't quite hear you. Excuse me.
I think it will work as well.
Yeah, I mean, it's kind of more or less the same, right? One is a regular object, L value. 2 is read only, and S normally, naturally, I should say, is simply going to get a reference to 2, and the observe function is going to observe or read from this input and generate some new information. What about 3? Observe 3.
It'll work as well.
It works. What is going to happen here? Well, 3 obviously returns what is called an R value. Okay. Again, it's quite important to understand that 3 returns an R value. It's a temporary. it is going to stay alive just for a little bit of time until the expression evaluates. So there is potentially going to be a copy, potentially, right? And so unlike 1 and 2, if 3 is a very large function or large piece of data, then S will become a reference to a copy of this R value. Okay. Same with 4. 4 is no different than 3. It just returns a read-only. We call this a const R value. And one of the reasons why sometimes people would do that is because in certain class-based functions, let's say the plus operator, right, for the string, it returns by value. And programmers can actually take that value that is returned by the overloaded addition operator, which is going to die very soon, and do stuff with it, right? And quite misleading. You can't, as a programmer, do that or shouldn't do that, but C++ doesn't have any safeguards. So some people kind of put the const, and so I don't see a problem with any of the observe functions. Now, mutate, as the name implies, is a function that takes what we call a in-out parameter, meaning that with S, you not only want to maybe read some information, but also update it, right? And anytime in HLP2 we had to change, we didn't know anything about move semantics and return by value, RVO, none of that stuff. So we said this is a good way to pass something that needs to be a big thing that needs to be changed. And one is going to return a R value. So is this function going to work? So this one. What is your opinion about that?
Yes.
Yeah, I think it should still work.
So 1 returns an R value, right? There's no address associated with that. And this is a temporary transient object. So can
one string object?
Oh, okay, okay. Sorry, what is it?
Yeah,
So
I think.
Oh, I'm sorry, I'm not catching you.
I thought one was a string object.
Oh, yeah. Sorry, that's kind of what I was about to say. You're absolutely right. For some reason, I was complicating myself with 1 and 3. So 1 is a regular object. So S is going to get a reference to that, and mutate is going to change 1. Essentially, that's what it is, right? Make sense? Because I'm getting confused with the function call and the definition syntax. So this, not a problem. Absolutely. Thank you. Now, what about mutate 2? Obviously, the answer is no, right? Because S is a reference to a plain string, but 2 is a read-only. So you're breaking the constness convention. So this is not going to work. OK, so what about mutate 3? So this is good. This is bad. So now what about mutate 3?
Not work.
It won't work, absolutely, because 3. Well, 3 is returning, a something by value, and that particular thing is an R value. OK, and by convention, according to the rules of C++, this guy cannot become or be made to be a reference to somebody who doesn't have a name, who is not permanent, so to speak, in the scope in which S is defined. So this is going to be flagged as an error message. So one of the things you should do after a class is over and you have time is to actually program this and see what kind of messages you're going to get. 4, obviously, if 3 didn't work, 4 isn't going to work. So out of this particular mutate, the 3 calls are not going to work and the first one is going to work. So basically, I think the reason why I put this quiz up is for all of us, it's a lot easier to understand why certain things work the way they do so that we can not only read code, but also write appropriate code, is to understand this whole idea of R values and L values. Because today we're going to start talking about something called R value references. So what I wanted to do was give everybody a primer on R value and L value references. My friend, somebody spoke.
Yeah, Professor, for observe tree, right? You called not the variable, but like you called like with an open bracket and close bracket inside. And
So
I tried compiling it, couldn't work.
3 doesn't work?
Yeah, cause you call, instead of calling tree, you call tree open bracket close bracket.
Well, 3 is a function. We are calling a function. This function will return a string that is got no name, but S.
Okay.
But S.
Oh, I get it. I understand. Because 3 is a function. Yeah.
3 is a function, yes.
Okay, thank you.
And 4 is also a function. Sorry?
3 is a function that returns a string, right? So
Yeah. So we are making a call to a function that returns by value. We are making a call to a function that returns by value. Here, the difference between the bottom observe and the top observe is that 1 and 2 are named entities, right? But 3 and 4 3 and 4 are functions that don't return things that have names. And that is quite important, especially when we get into move semantics. So what I'll do is quickly kind of show you some of the things. Normally I cover this in HLP1, but very basic. Actually, I just completed it because I'm teaching HLP1 too, but at a very basic level. And after that, HLP2, we don't have an opportunity to talk about that, so this will be a good primer, okay? So let me start at the very beginning, in 50 years back, which is. So C, they were designing the operators, the expression tree, the parsers, the grammar, and basically they had to come up with a way to explain why certain expressions could show up on the left-hand side of the assignment operator and certain others could not. For example, the circle ones, A, B, C, are good, but 30, which is a literal, cannot show up on the left. So they came up with the idea of what is called every expression, right, is going to be an L value or an R value. L value, which is, I believe, a shorthand for left value, is an expression that can appear either on the left or the right hand side of an assignment. So A, B, C are variables, and notice they show up on the left and they show up on the right. R values are simply those expressions that can only appear on the right hand side. Those would be these functions that return by value and literals. They can show up. And it's quite important to know this because I'm sure many of you have read some compiler messages where even if we want to ignore this whole idea of L value and R value, they spit out these messages, L value, R value. So it's good to know. All right. Now, all of this worked well until 89, at which point or 98, I can't remember. But basically at that point they added C98, the const qualifier. C++ was using it, so to make C and C++ be a little bit more compatible, they added the const. Suddenly, with the addition of const, the old definition of an L value doesn't make sense anymore because C cannot show up on the left, but it is an object that has a particular location in memory and it has a name. So they came up with a slightly different definition of what an L value is. And it's basically a shorthand for a locator value, which is any expression that refers to a particular identifiable memory location. And for R values, they simply said by exclusion, anything that is not an L value is an R value. So R values would be, for example, these guys. Anytime you call function 3, well, that is an R value. Anytime you call function 4, well, that is an R value. So R values are just the kind of like the temporary results we get when we evaluate an expression as part of a larger expression tree, and they disappear at the end of the sequence point associated with that particular expression. So that's all good. And the confusing thing for quite a lot of people is that you can use an L value where an R value is required, but unfortunately we can't use an R value when an L value is required. It's kind of like L values can show up everywhere, but R values can only show up on the right-hand side. And that's why I think it's useful to kind of start shifting towards the C++ model, which is every object, in this case, a simple integer, there are two numbers associated with that integer, right? One is the values that is associated with X, and the other one is the location value, the address where this particular variable is given storage. So in certain contexts and certain expressions, we are interested in this. In some other cases, we are interested in this. When you are interested in this, you are looking at the R value associated with this guy. When you are interested in this, you're looking at the L value. So here, for example, we are interested in the location value. Where exactly is X? Stored in memory, or what exactly is X a mnemonic for? And in the other situation, we are interested in the other value, which happens to be in this example 99, right? So basically, what I do is I sort of explain from a C perspective, L values and R values using this sort of a table, right? So when X shows up, the variable shows up on the left-hand side, think of the address. When it shows up on the right, think of the value stored at that address. Anything that shows up in terms of the address, then think of it as an L value. Anything that shows up on the right, think of it as an R value. And here we can kind of pause and think to ourselves, anything that has any expression that is an L value must have some sort of a name associated with it, while anything that is an R value doesn't really need to have a name. For example, y plus 30, right? This is an R value and there is no name associated with it. It's just simply the result of an expression. And so again, L value means X's memory location, R value means the value of Y. The other important thing is that L values are known at compile time because the compiler is the one specifying storage for all of our variables. While R values, the data that is stored in these locations, well, that is going to be dependent on the runtime sequence of instructions that make use of this particular variable called X. So these are the sort of like the big differences. Generally, they hold in C++, but you kind of end up with some sort of like deviations, right? And the other thing about L values and R values is that they help you understand how operators work. For example, pre-increment, post-increment, the assignment, the condition operator, all of these, if you actually look at the precedence table, they tell you what kind of an operand is required. Does it take an L value or an R value? And what is the function, the operator, the black box, spit out? Does it spit out an L value or an um, um, R value? Right, we'll talk a little bit more about that in a moment. Function calls, okay, generally are R values, but in C, functions can return pointers, so they can show up on the left-hand side and therefore can be thought of as being L values. So I have this function that returns by value, this function returns an address. And this is okay, this is okay. Obviously, this is not okay because this evaluates to the result of that function call expression, which is a value. And since there is no name associated with this, no address, the compiler will flag this as an error and you'll get something like L value required on the left-hand side or something like that. But this one will work. Why? Because this, if you think about it carefully, evaluates to a particular location in memory, right? It is like an alias for this particular variable, GI. So rather than using GI, we are indirectly using GI. And we can actually write more complex expressions. This one, assuming that the precedences are always correct. Basically, we are calling this function foo. This function foo evaluates to a pointer. We are dereferencing that pointer that gives me the location associated with some object, some integer object, and I am incrementing. The only thing you got to make sure in these scenarios is that this function does not return the address of an object that is no longer alive, no longer in scope. And so I made sure that I returned the address of a global variable. In C++, things became a little bit more complicated because obviously we had function overloading. And because of function overloading, a lot of operators changed their behavior, right? In C, you could not do this, right? Prefix to some integer object, say I, but in C++ you can. The behavior was simply because to kind of make these operators be more adaptable to function overloading. So here's an example. All of you know about overloading the subscript operators. So what shows up on the left-hand side is essentially a named object, except that particular named object is sort of encapsulated by some other object, in this case S. This is obviously an error because C is a function that gives you a read-only reference, and so that, you're breaking the constness. But then the weird thing about the C++ that I was speaking about earlier is that if this guy overloads the addition operator, then the addition operator returns by value. And so S plus T evaluates to a string object. That particular object is going to be only alive until this sequence point. After that, it dies. But within that period of time when it is alive, I can do some weird stuff, which is change that particular object that is going to die, right? And so nobody can actually see my changes, but I can still do it. And for that reason, in those days, the practice before R value references was to sometimes return. Where is the function? 4. Sometimes people return by a return const values simply because the guidelines, most of the C++ guidelines said, you know what, don't make your programmers, when you write your classes, be able to do this. So therefore, if the addition overload returns an object, a read-only object, then this will be marked as a compile time error, right? So all those have gone out of the out of fashion, but if you do see them, then you will understand why. So these days, nobody actually returns a read-only value, but you can still write code like this. All right. OK, and why people stop returning read-only, we'll talk about that later. Now, the other complication is that we can, as we saw with the subscript operator, we can return references. So you can actually see all kinds of, for C programmers, bizarre code. So it looks like this looks like that, and bool can show up either on the left or the right. You can apply the address of operator. So it's almost like an integer object, right? So bool is simply a function call that returns an alias to some other object. And so anywhere you can use that other object, you can use bool. And so bool shows up everywhere, both on the left and the right. And so things changed a little bit up until C++ 11. So in C++ land up until 2011, the L value expression was essentially referred to as any object that kind of exists in a wider scope than a particular single expression. So a variable that is defined at a particular location in a function, well, it is alive until the scope of the function ends. So that is what I mean here. So in those scenarios, we think of that particular variable as an L value expression. R value expressions, we think of them as transient. They are completely temporary. They evaporate. They go away at the end of a, the sequence point of a particular expression. And so they are generally literals or temporary objects that are created in the course of evaluating the bigger, larger expression tree. So think about, for example, the behavior between these two guys. If you recall, this is the prefix and this is the postfix. What does the postfix do? Well, the postfix bumps up the value of whatever it encapsulates, and it returns the persistent object. In other words, X. X is alive throughout the duration of these expressions. And we are simply returning when we make, when we write an expression like this for sum, where X is an object of some class X, it doesn't really matter because this means X. All right. On the other hand, all of you, if you recall, this guy makes a copy, then bumps up the persistent, the original X, and then it returns the copy. So the value that is returned by this guy is only going to be alive until this particular expression is alive. As soon as that sequence point associated with this expression is reached, that particular thing evaporates. So that's what we mean by persistent object versus an object that is transient. OK, so that's how people started thinking about L values and R values. L values are things that exist in the larger scope. R values exist in a very sort of transient manner. And remember, L value and R value are really things that deal with expressions, not, for example, a function foo, right? If I declare this, then we don't say foo is an L value or an R value. All we care about is how is foo being used in an expression, right? When it's used in an expression, since it returns an int, it evaluates to an R value. That's all there is. So we don't actually think in terms of L value and R value without expressions. So just kind of, wind up our discussion on L values and R values. X is a name of a variable, so it's going to stay in scope. So we think of it as an L value. It is persistent. There is a name X, so it means that that particular name is a mnemonic for some address. Same with PX. It's a mnemonic. It's a name. It's going to stay in scope for a while. This is a declaration. So there's no such thing as L value, R value associated with this particular declaration. Obviously, again, S is an L value. Now, when we make a call to foo, what we are doing is we are calling foo, and the argument to foo is this particular object, right? And when foo is in the definition of foo, S is the parameter, and there is going to be some sort of a copy that is going to be made, and that copy is only going to be alive as long as this expression is alive. When we reach the semicolon, the sequence point, that particular temporary is going to get destructed. So this guy is returning by value, but this is an L value being assigned the new value returned by foo. Foo returns by value. So this hopefully will help you understand the observe and the mutate functions. Foo returns by value. So the compiler is not going to like it if you try to think in terms of an L value associated with that expression, right? So foo is something that returns a value. When you apply an address of operator to something that is transient, the compiler is not going to like it. You can only apply the address of operator to things that are persistent because they exist in the program memory, and they're not going to just go away at the end of this particular expression. Does that make sense? So this is incorrect. Now, same idea here. This is assuming non-explicit function constructors. So foo is being called with the C-style string. So the argument S, the parameter S is going to be constructed so that it encapsulates this, right? And that particular temporary is only going to be alive until this particular sequence point. VI, vector, it is an L value. This is an L value because this particular operator overloads and the overload of the subscript operator in the vector class returns by reference. And so as far as the compiler is concerned, this is an alias for the sixth element of some memory that is encapsulated by this particular class. Foobar is a function that we are declaring. So foobar is neither an L value and R value, it simply is a declaration. So now in this particular call, we are treating foobar as an L value. It is an L value to some location, that foobar is a synonym for. The only thing we hope for is that foobar doesn't return a reference to somebody that is already dead, right? So let's suppose that that is not the case. Then in that scenario, this is good. Foobar, again, we are making a call and the return value is an L value. So PX is essentially going to be the object that PX is pointing to is going to be updated with, whatever value that this guy represents or is an alias to. So that is the basic idea. Whenever you are dealing with L value, R value as in literature in your textbook or online, then another way shorthand is Well, is an expression L value? One simple way for you is, can you get the address? Can you apply the address of operator? Because C is C++ is very strict. It only allows this particular operator to be applied on L values. And these L values generally, can be something that you can easily kind of get a sense of. So if A represents a vector, a string, or some other container that overloads the subscript operator, then you should understand that this is okay. Pointer is a pointer variable that points to some object. This is that particular object that pointer is pointing to. So clearly you can apply the address of all these other things. Generally speaking, the compiler is going to flag them as an error, and reading the declaration of this overload and this particular function, you kind of get a sense of what is being returned by that function. If they are returning an R value, in other words, by value, then you know that you can't apply the address of operator to those expressions, and therefore, by exclusion, it is not an L value, and therefore it must be an R value. Okay, so that is kind of mentally how one can figure out. And why does the compiler put in this rule? Well, basically, if you take the address of some temporary guy that is going to die at the next sequence point, then it's going to be really hard for you and me to write proper code, because we're always fighting to figure out what is alive and what is not. So instead, they're quite strict. The other thing you need to kind of also understand, because that is going to affect a whole lot of how you write your functions, is non-const and const values, L values. So notice this particular definition, guys, S1. I think of it as a modifiable L value. Why? Because you can assign to S1. You can change S1 to your heart's content. You can pass it as an in-out parameter to a function that can read the contents of S1 and change the contents to. S2 is non-modifiable L value. So we think of it as a const L value. You can use it anywhere you can use S1 except on the left-hand side. Okay. So in other words, it is read-only. Now, function F1, we think of it as a modifiable R value. Okay, that is quite an important term, right? And that is where the people who invented R value references sort of took off. They basically said, hey, imagine you have this function F1 that returns this R value, right? A temporary. If there is a way to capture it through a reference, then we should be able to change it because it contains something that we want. And it's going to die soon because it's a temporary. So if there is a way for us to grab that thing, then we can actually improve the performance of C++ programs by easily 20 to 40%, right? And so these were always called modifiable R value because you could always play around with them, but there were no proper semantics available for you to actually keep them alive until you are ready to kill them, because otherwise they die, right? As soon as the sequence point is reached. In other words, whatever is the value that is returned by F1 is going to die right here. But if there is a way for me to keep that guy alive so that I can actually make use of it and then sort of let it, die as sort of like a peaceful death after doing some good for me, then that is essentially the essence of what we are going to talk about, right? A modifiable R value. You can also have a const R value, and they're not of much use, as you can imagine, because by the laws of C++ and the laws of the keyword const, there's nothing you can do to F2. Even if it contains something valuable, you can't change it. So from the perspective of programmers, F2 is the least interesting, right? Because it returns a R value that is going to die, but there's not much anybody can do with that. So as I explained in the old days, people used to return const R values simply because they didn't want programmers to trip over themselves and write code that they believed would have lasting effect, only to find out that that particular object was going to die. So by making it read only, then any changes made to that particular object would be signaled by the compiler as compile time errors, right? And so the programmer can fix it. And we'll kind of look at them, but they're not that interesting. These guys are for our class today. Okay, so running through, well, all of us know what reference to X means. This is something that you've been using HLP2 quite a lot. And I'm going to kind of make up quite a bunch of questions related to references and so on for the midterm, right? So make sure you kind of understand references well. So again, I'm not going to cover anything more than a couple of slides. So X is obviously an L value. Notice modifiable L value, that's what I mean. S1 can be changed as much as you want because it's a named object that is in scope. So X is an L value, Rx is simply going to be a reference, modifiable reference to X. So using Rx, you can do whatever you want, whatever you could do to X, right? For example, all of us know now that when we write code like this, we are changing the object that Rx is an alias to. We can initialize anywhere you can use X, you can use Rx. And same idea, we can apply the address of operator. Well, you're actually getting the address of X. So in this sense, when people use the term reference, I think maybe a better term would be alias, right? That is what you're doing. A better pointer internally, okay? When you write this definition, remember, Rx can only be a reference to. So what do you guys, anybody can hazard a guess if you were working in Microsoft in the Visual Studio team, working on the C++ compiler, what would Rx be implemented as internally?
Pointer.
Is that enough? Is that enough?
Const pointer.
Const pointer. So Rx, think of it as a read-only pointer to an int. What does that mean? Well, when you, because it is read-only, it needs to be initialized, right? So that's why references must be initialized. Remember, they're better pointers. They need to be initialized because they're read-only and they are pointers to an int. And once you initialize Rx to point to X, that's it. It's gonna, until it dies, it's only going to be a pointer to X. The only thing we need to make sure is that X doesn't die before Rx, because then things are going to be bad. So the important thing for us is that it binds to modifiable L values. Again, guys, if you haven't written down on a piece of paper, write down, because I'm going to use these terms. Modifiable L value, S1, const L value, S2, F1, modifiable R value, F2, const R value. So what can you do? Because obviously we are interested in writing functions. So we don't deal with dinky little references like this, right? We use references to move around large amounts of data. So they can be bound to objects that are modifiable, L values. You can't bind them to const L values because obviously you're breaking the built-in rules associated with constness. You can bind them to modifiable R values because, again, it's going to be a program problem if the program changes things that are going to disappear, right? And you can bind them to const R values. So these were called references in HLP2. From now on, we're going to call them L value references, okay? Because we're going to talk about, obviously, R value references. So main purpose is to refer to objects that we wish to change, move around large amounts of data. I think of this as in-out parameters. Foo, something big called X of type X is being passed, and this function is going to take a reference so it can read the stuff, but it can also change it. That's why it's called in-out, inside outside parameters. OK. So they must be initialized, no such thing as a null pointer, no operator operates on a reference. When you saw me apply the address of operator on Rx, you're not operating on Rx, you are simply an alias to X. All right, and well, we saw that we can change what our reference refers to. You can get a pointer, you can define an array of references. So basically, don't think of a reference as an object, right? They're simply aliases to other objects. So they are like pointers, but pointers are objects, but references are restricted pointers. OK, let's just run through these examples. I have a whole bunch, so I have to run through them with you. I and I2 are modifiable L values. They're ints. R is a reference to an int. R2 is a int. I3 is a modifiable L value. Ri is a reference to that modifiable L value. R3 is a reference. R4 is a reference. This is incorrect because R5, remember we declared R5 to be a pointer. It sometimes helps guys to actually dig underneath because mentally you have this image now. Hey, R5 is a pointer. Can you get the address of 10? No. So R5 cannot be a pointer to 10. Right? Makes it easy. Then this guy is an R value. It is ephemeral. It vanishes as soon as the sequence point is reached. So when it evaporates, what is R7 going to point to? So therefore, the compiler will make sure that you can't make an alias out of an R value. The compiler is also not going to allow this, where a pointer to an int is pointing to a double object. And finally, a read-only pointer to an int cannot be made to point to a read-only int object. We'll talk about that in a moment. Some of you may be thinking, why can't R values bind to references? I sometimes used to think about why. And the simple answer is, take a moment to look at this function foo. You're calling this increment function, okay? And D is as you can imagine, a modifiable L value. And in your mind, you're thinking, I'm not interested in changing D. What I would like is to create a temporary int that contains the value 10. And then I update that 10. Maybe I can return that 10 that becomes 11. The reason why C++ doesn't allow you to do that is because it is confusing as heck. All right. I mean, am I changing D or am I changing the value, the R value associated with D. So is this expression an R value or an L value, and it all gets confusing. So the rule is R value is what this is considered to be, right? So non-modifiable const reference to X. So it can bind to modifiable L values. It binds to const L values. Here's the good news. We can actually use these guys to extend the lifetime of those things that we said evaporate. Right? Sure, the sequence point came and went, but since this guy is now, some guy of this type is being made to become a reference to something that should have died, we can sort of make use of this. And obviously we can't really change it because this guy is a reference to a read only, right? So we can modify it, but we can extend its lifetime. And it also binds to, without any surprises, const value. So this is the reason why when you wrote code in HLP2, this was considered to be the best way to write functions. Functions that take non-modifiable const references, right? You can throw any argument at them and they all work, right? Without any surprises. You can send an L value, you can send a read-only L value, R value, and everything stuck. And most of the functions that you wrote this way, you probably never encountered any trouble. All right, so this is generally used to describe what is called an in parameter, okay? An input parameter potentially meant for reads, and then I read some stuff and do other things with that information, but I cannot change it myself. We generally refer to them as input parameters. So this guy, RCI, okay, is going to be declared like this. Remember, we talked a little bit about complex declarations. I just don't want you guys to forget about it. So RCI is read only. Why? Because it can only refer to one object and no more. But the object that you are referring to cannot be changed. Maybe the object itself is a modifiable L value, but not through this alias. And here, right, we are not actually making this guy be a pointer to one. What really happens is the compiler is going to create a const object called temp1 or whatever you want to call it, initialize it with this value and make RCI point to temp. Make sense, guys? That is what happens internally. You can read the Stroop's, I forget, this was a book he wrote in the late 90s, about the design of C++, and this is how he talks about implementing references in that language that he wrote. Does it make sense to everybody? Okay. So this is not going to work because obviously, you know, RI is a reference to a modifiable integer. So quite important that you memorize this particular table. Notice a reference to a read-only X can be made to bind to any one of these guys, pretty much anything that exists. So it means that this will work, right? This will work. This will work. And this will work. Nice. Do you guys see that? And here's the other beautiful thing. It actually, even this works. With 12.5 cast to an int stored in a temporary object, and this guy declared to be a read-only pointer to a read-only int that contains the truncated 12.5, which is now an int, and RCX5 is going to be made to point to that guy. Okay. All right. So this is quite an important point. Initializer for modifiable const references need not be an L value or even of type X, can be pretty much anything. And that is what I was talking to you guys about. So in parameters, main purpose of const references, and I hope that is what you've been programming, right? Mostly, most of your work happens with these kinds of things. Okay, now here's the how do I say this? Existential question. No, I can't pronounce it. Forget it. A reference, right, is a name. And can we speak about this particular reference being an L value or an R value? Do you guys understand what I'm talking about? So what I'm talking about is maybe I have something here. I'm talking about let's suppose you're writing a function foo, and that particular function has a reference parameter. And is that parameter an L value or an R value? Maybe that is exactly what I'm asking. You guys understand what I'm saying?
Can say again.
Okay, maybe actually I'll why don't I write it down? Right? Obviously, I'm not making much sense, and let me which one is the visualizer? Let's hope this is the one. So I have some examples here. Okay. The basic idea was, is a reference a name? And can you argue about whether that particular name is an L value or an R value? So let's make an example that I have written down in the slide. Right, we have can you guys see? Okay. Then I have a function, let's say f1, that returns, let's say, Texas. And then I have a function that returns, let's say, something like that. Okay. So far, so good. Everybody understands there are 4 functions. Now, I have a function called test. And this is very similar to the function that to a const reference that we have been dealing with. Okay. And this inside when we make a call to this particular function test, okay, str is a reference, and you can take the address associated with this particular name, even if you call test with functions that return L values. For example, look at this particular expression or this expression, right? This evaluates to an R value. All of us know now that this is an R value because it is temporary and it's going to die as soon as the function call terminates. Now, yeah, now this guy is going to return some string. str is going to become a reference to that string. And inside this test function, I can always apply the address of operator and get this particular name's address, right? Or the object that this guy is referencing. Am I making sense? So clearly, this guy, irrespective of whether it's referencing an R value, R and L value, which is what happens when I make a call to test S1, str is always considered to be an L value. Did I make sense? So inside the definition of test, str is a const L value and its address can be taken and used before test returns. This is true even though test is called with R values that are returned by F1 and F2. So for example, when you call test directly like this, then a temporary string is going to be constructed. And this str is going to be referencing that temporary string. And we can always get the address associated with this object in the scope of the test function. So in that sense, I think of str as an L value. And I hope I'm conveying sort of not some sort of quirky thing, but it's quite an important thing. And if you don't quite understand what I'm trying to say, that's okay. I'll give it a further shot later on. OK, but the important thing is that this guy, because of the nature of its declaration, can be made to be a reference to L values, R values, and everybody, right? And so what does that mean then? When this guy is referencing or is bound to R values, should we think of this as an R value? Or when it's bound to things such as S1, should we think of this as an L value? The answer is very simple according to C++. This is a name and therefore this should always be treated as an L value. Right, and when you apply the address of operator to this guy, you're going to get the addresses maybe of these temporaries, but they are valid addresses until the scope of this particular function, which is when this guy goes out of scope. So the basic idea here is that L valueness and R valueness is a property associated with expressions, not with objects. So don't think just because this guy is going to be a reference to an R value, this somehow becomes an R value. R should be treated as an R value in a reference, in an expression. It's always going to be an L value because it has a name. Okay. Have you ever bound an R value to a const reference and then taken its address? How frequently do you guys write functions? Yes, you have. And sorry.
I was trying to answer the question, but then you were going on.
Yeah, I was simply going to say we have done it often in HLP2. Consider this particular class.
Yeah, it's like a get function that const, right?
Yeah, I mean, actually, I was thinking of something much more simpler, not even get, something that we normally tend to do quite often. So this is the sort of like the copy constructor, right? So we're not interested in this. I just wrote that. And then we have the copy assignment. I'll label it as RHS. Do you guys recall? One of the things many people talk about is I did introduce the copy and swap idiom. But if you didn't have the copy and the swap idiom, the other popular idiom that people use is if the address of the object that is calling this particular assignment overload, it's going to compare for self assignment with the address of this guy. Do you guys recall? Check for self assignment. I've seen many of you do that, even though I've told you not to do it, but that's OK as long as it works. And now let's suppose we have a factory function called foo. It spits out widgets of type X. And I have, X1, X2, let's say time goes on, X1 and X2 have changed, and then I assign to X1 the value that is returned by this function foo. This is an R value. Everybody agrees with me? Nobody agrees? What's going on? Come on, guys.
Yes.
And RHS is going to be a reference to that R value. And we can take the address associated with that R value. So what have we done here is that we have extended the lifetime of something, right? Which would have died, except we have made RHS be a reference to this guy. And that guy has no name. It simply is a value. And we have extended its lifetime and we are doing some fun stuff with it, including making queries about where exactly it is located in memory. So the answer to our question was, of course, absolutely. Have you ever bound an R value to a const reference and then taken its address? Yes, this is the example that we have just seen. OK, what can we do with modifiable R values? As far as you're concerned, up until HLP2, not much, right? You can bind L value reference to modifiable R values. You can't assign things to R values. All you can do with these modifiable R values is make const references, as we just saw. Can they really be modified? Well, in C, there is no way to get access, right? Unless you do some really low level stuff, which is down to the processor level, right? You need to know where and how things are being moved around. And it's easy to know if you're an assembly programmer. There is an entire dance that takes place between the caller and the callee, but generally not open to general programmers. C++, not so until 11, right? Calling a non-const member function on a modifiable R value was allowed in C++ 98, which is what made many of the guidelines say return. If you're returning by value, for example, the overload to the, some of you may have seen blogs or whatever, really old references. What they tell you is that when you apply the overload to the postfix, it generally looks like this. You return by value and you write it like this. I think you pass an int that doesn't do anything, right? To distinguish it from the prefix. That's my recollection. It's been a time since I wrote the postfix. Then you get in here, and one of the things we do is we say, okay, I'm going to define a temp that is a copy. So I've created my copy, right? And I return the copy that contains the old value, but in between, I take this object and presumably apply the prefix, right? You don't want to do this because then you're recursively calling yourself, but this should do the trick. And I can recall the precedence order. I think this is higher, so you could have written this like this, not a problem if we are correct about our precedences, but since I'm not sure, so I wrote it like this. So this makes a copy, this bumps up the original, the persistent, the X that is invoking this particular function, and then you return a temp. So you're returning by reference, right? You can actually do bizarre things like this. You can make this be on the left-hand side. That is what I was trying to say. So the general guideline was always return a read only. So then as soon as the programmer did some funny stuff like this, the compiler would flag this as an error because this entire expression evaluates to a const. So that was the meaning of that. Hang on. Sometimes I have so many icons. It's like my whole desktop is an open book. All right. Let's see. Where am I? Where am I? Where is my PowerPoint presentation? Oh, yeah, here. Okay, excellent. All right. So let's move on to what we can do with this in 11. OK, so now, hopefully, when you go home, you should think about these things carefully because I have more of these where they came from. OK, I'll hold them tight to my chest until I'm ready to kind of give you an exercise. All right, before we do anything, OK, I don't want you to forget why we are here. All right, I'm not interested in RVO. We already covered that. RVO is really cool. Turn it on, and it's better than anything, right? Better than move, better than anything else that C++ gives us. So the problem here is that we are not interested in RVO. It's not going to work because we are going through an assignment. RVO, as the name implies, okay, it's a return value optimization when you're constructing V. But if V is already constructed, the return value optimization can deal with destructing and getting rid of all the resources that V has. If you're building V, then RVO will say, hey, rather than building something and then making a copy of that, I'm going to build it for you directly, right? And it works beautifully. We saw that, and it saves a whole bunch of stuff. But that is not what's going on here. We still are going to get the advantages of RVO, but we still have an assignment, just the plain old copy assignment that we have dealt with. So what do we need to do in terms of using R values to improve the behavior of this code, right? So we saw this the previous day, and we define a vector. It's reserved 3. So reserve means the memory is uninitialized. Vectors allow you to separate construction versus memory allocation and construction. Okay, pushback, there's not a whole lot to do. Pushback, emplace back, it doesn't matter what it is, you got to make a copy because that is the value semantics. Vectors are supposed to be as easy to use as an int, okay? And ints, when you when you assign them, they get their own value, right? So the same idea here. They employ value semantics. Next class, we're going to look at things that don't employ value semantics like smart pointers, right? Now this is going to go through some complicated dance, and it's going to construct an unnamed object somewhere on the stack, okay? And that object is allocating memory, and you can see that, right? So it's quite important that so far that we don't do what we have done so far, which is we just call pushback, and because the classes that we are building, not the vector class, not the string class from the library, but some of the classes that handle resources that we have been building, they don't deal with these R value references. Notice the fact that S plus S is an R value. It is ephemeral. It's going to go away as soon as this function gets evaluated. So what pushback does is what pushback does, which is make a copy, because this particular class. Hey, somebody eating chocolate early in the morning, you know, the wrapper, the candy wrapper. Us at Chips, bit too early for both. All right. So this guy, you know, he doesn't know anything about R value semantics, right? It's HLP2 level. So what happens then is that it makes a complete copy. And this guy, just like any R value, as I indicated to you, is going to die. And that is what this whole thing implies. It goes out of scope at this sequence point, right? It is ephemeral. It is a transient. And we made an unnecessary copy. Okay. This is what we want, right? We understand the behavior of R values, and we keep those R values alive for just a little bit longer using references. And then we kind of come in and take over some of, you know, the resources that they have claimed for themselves. And that is the reason why we are doing all of this, because they have something that we need, right? And so that is exactly what this picture is indicating. Finally, what this means is that the object goes away, right? Notice it has the null pointer. So when it goes away, it is going to be sort of well destroyed, right, by the destructor. Here's the other cool thing. In some cases, we have an L value. S is an L value. It has a name. But we know it's going to die. It's going out of scope. So what I would like to do is take over its stuff rather than make a copy of somebody who's going to go away, right? And that is what the move function does. It doesn't really move anything. It simply tells the string object or the string class that treat me an L value as an R value. That's it. All right. And it's unfortunate, but you know, move doesn't move. So all move says is, hey, I am L value, but treat me as an R value. What do we do with R values? Well, we grab their stuff and sort of, send them to the gallows, so to speak. And that's exactly what has happened here. All right. And that is what is the motivation for our value references, right? Because we need a way to distinguish between this and this. Here we are providing, the regular uh, uh, copy or constructor overload, which is copy by value. Here we are saying, no, we don't need to make a copy. Instead, the vector class, why don't you take over somebody's resources that are going to go away? And who's going to do that work? Obviously the string class, right? Because this is a container that is going to contain string objects. So that is the essence, right? It all comes down to making sure you square your, your knowledge about L values and R values. And once we get here, notice R value has done its work, okay? RVO has done its work. Why? Because this guy did not make an entire copy of itself, which in turn was used to, assigned to V. Instead, what it's saying is, I am the return, right? So RVO is actually doing the work here. And what we are doing is we are making a copy of this object and we are making a deep copy. And the deep copy entails copying all that stuff, which of course is not what we want. So if we perform the deep copy, notice there's a lot of killing going on. And what we really want is simply a shallow copy. Shallow meaning I want to take this guy's data, 2 data members, right? Copy them over and set them to some value, and that's it. And those are move semantics. And ultimately, even in this tiny little program with just 3 strings, we have saved one entire construction destruction here. We have saved one entire construction destruction here. And the 3 objects no longer needed to be copied, right? So we're not, we are saving 5. So roughly speaking, every time you end up with n number of objects in a container, you're essentially going to save 2 times n, right? First to construct that stuff in a function and potentially return. And return by value is the best way to return simply because of the return value optimization. It's even better if you are able to do it like this, right? Then this is going to be V. That's what we learned about RVO. But this, unfortunately, is assignment, and it happens. But even then, take advantage of return by value. All right. So enough with these pictures, but you hopefully now have a very good idea of what it is that we are interested in doing. So let me quickly run through the remaining slides. I may not get to the code, but I'll be done. So this is the beautiful thing. At the end, we are in the same state as without using move semantics, but with something significant gain. Assuming RVO, which is always going to happen if you compile in 17. Avoided 5 unnecessary copies, which was quite a lot because all we were dealing with was just 3 strings. Assuming your str class implements move semantics, right? Able to now use vector of strings naively like a built-in type. You don't have a problem returning ints. In fact, it is an important thing. When you pass and return, you don't use references and so on. Instead, you pass and return, right? And so now we are able to do that using vectors because even if your vector contained 1,000,000 elements, the cost of returning it is just going to be 16 bytes worth of stuff. That's it, right? So it's quite nice. And returning big things is no longer a performance issue. And my understanding that I read is that as soon as people kind of changed the way they wrote their classes and made good use of the standard library, some of their code started executing 30% faster with Move Semantics, right? But again, everything has to be carefully measured. So, but there is ample room. So how does all of this work? We know somehow it is connected to that R value stuff because modifiable L values, we know how to take advantage of them. We know what to do with const references. So the only thing left is that R value stuff. So how do we get help from C++? Because it must, know about these things and take advantage of them. And it's sad that it took until 2011 for them to do this. Okay, so this is the copy assignment. All of us know how to write this. We have done this. We know what we are doing. We are cloning. We are performing a deep copy. This is this is the copy assignment. This is the copy constructor. Same idea, right? We are performing a deep copy. So all of us know about this. And I just want to illustrate with pictures. This is what we want to do. S1, S2, L values, S3, L value, which is being constructed from S1. What do you want here, guys? You want copy. You don't want any of that fancy move stuff. Why? Because S3 and S1 are both L values, and we want S1 to have a long productive life. We don't want to, get it ready to be sort of sent off to the gallows. So therefore, all we can do here is make a copy. Same thing here. S2 is a L value. It's going to be alive for a long time later on. So we want it, to be simply a clone. And so in terms of pictures, this is kind of what it looks like, right? Basically, S3 is going to give up the old memory and essentially point itself. So this is the cost of doing business, as they say. Now, I'm showing you the addition operator that all of us have written. As you can see, it returns by value, right? So the return object is an R value. And there are many overloads of this, so I'm not gonna worry too much about the general thing. I just wanted to show it to you because now S4 is going to get initialized with this. Let me first say, right, whether you have move or not, S4 will get initialized with temp. We saw that with RVO. That is the cool thing about RVO, right? So move semantics don't actually play a big role. You are actually better off making sure that you don't worry about move at all. S4 will be constructed by the compiler as though it was temp. That is the beautiful thing. So S4 is generally constructed for free, but if your machine doesn't have, your compiler doesn't have return value optimization, then the picture will look like this. Notice this entire thing created there, and it says here, this is not what we want, but this is what will happen because we are making a copy, all right? And then we are killing off the R value. Then this guy comes alive again somewhere on the stack, and we call the copy assignment. And what it does is that it kind of makes this guy point here, then it gives up this memory, and then it gives up this memory. So there's a lot of unnecessary stuff going on. What we really want is this. This is, the basic idea of what we want. S4, irrespective of whether you have RVO or not, let's say using move semantics, all I want is S4 to point to this guy, and this guy goes away, right? Similarly, the addition overload is going to go ahead and build this. There are going to be two calls to the overload. because the addition overload only takes 2 operators. It's binary. So it builds this, right? Then S4, which is pointing to this, is simply now going to point to this. And we'll make this guy point to that. Actually, I'm probably sure I have better pictures than my scribbles. So there we go. That's it. Some people write it like this, others write it a little bit differently. The main thing is that from the language's perspective, you know, this temporary object should be able to destruct, you know, making sure that all of the memory is reclaimed. That's it, right? And all we have done is, you know, there's no unnecessary cloning. So moving is dangerous when source is L value, right? We want to copy. Moving is safe when source is R value, because, you know, this guy is going to die. This guy is going to die. So what we want from the language, okay, is when we are using R values, then we want to use our HLP2 copy constructors. When we are passing an R value, we want this exchange to take place, right? And so the help we need from the compiler is to provide us with an overload that allows us at runtime to determine, oh, okay, the call to this particular function, because the addition overload is a function, is returning an R value. So we are going to go ahead and call the move assignment. In this case, actually the move constructor, not the move assignment. So what is that mystery type? Well, no prizes if anybody says R value references, right? So it has to be a reference type because the copy constructor and the assignment operator were invented in the 80s and the 90s to take ordinary reference. So now Strustrip can come in and the committee can come in and change everything. So it has to be a reference, and the mystery type must be able to handle R values, while the ordinary L value references are able to handle L values. So this mystery type is called the R value reference, right? And how do we declare it? If X is a type, then you get an R value reference using 2 ampersands. And not to scare anybody, but you get later on in the semester expressions that look like this, especially with templates. So if this is sort of confusing you, make sure you read up. The textbook has enormous discussion on this, but in the future we're going to talk about things like this and it can get confusing. So if X is any type, then this is an R value reference and the behavior is exactly opposite of L value. It can only bind to an R value, not to an L value, of course, right? Yeah, otherwise things will get screwed up. So here's an example. This is a variable and this is a function that returns an R value. So R1, R2, R3 are L value references, right? So R1 obviously can be a reference or can be made to bind or bound to variable. It cannot be made to bound to an R value because R2 is an L value reference. And likewise, R3 cannot be made to bound to a temporary, which is an R value again. Notice R values are completely opposite. This R value cannot be made to be bound to an L value. So that's not going to work. And R value can be made to be bound to the R value that is returned by this function. So in other words, this is a mechanism that allows you to extend the lifetime of this ephemeral transient thing, right? It allows RR1 to provide some sort of life support to that guy who would have died otherwise. Same goes for RR3, right? RR3 is going to be a reference to some unnamed temporary guy that just got initialized because there is no explicit constructor using this C style string. And obviously this is also going to be something we have noticed is correct. So a const reference can always be made to point to a temporary. So that is the behavior, right? So in mentally you're thinking, hey, the only cool thing about this is that it extends the lifetime of things that would have otherwise be dead, right? At least mentally, that's how, when I first learned of them, that's how I kind of conceptualized them. And the other beautiful thing is that there is no constness. So you are free to use these references to change the R values that they are referencing, right? And basically the key word here is that we want to do a destructive read for optimizing out a copy. Instead, rather than cloning a deep copy, I can take what you have. And so we can read write essentially. And if you ever come across R value references, don't worry. They look exactly like any other reference. And trick question, is S an L value or an R value?
L value.
Okay, that's very good. Everybody make sure you remember this, because some people get confused. S is declared to be an R value reference, but it is still a thing with a name. Got it? And anything with name, remember in our early discussion of an L value, that's why I went through the primer, is an L value. So in this scenario, S is an L value, even though it is declared to be a reference to an R value. So why do we have all these different things? Well, now you know. L value references modifiable. We call them in-out parameters, right? They are things that you want changed, and passing them by value will mean unnecessary copy. And so therefore you certainly want to use references, and that means you are going to be able to change them. So in and out, input, output. Const, well, basically you only want them to be read, right? We can't change them. So that would be input parameters. R value references, think of them as will move from to refer to objects whose values we don't need to preserve after usage. So I'm doing stuff, and rather than perform copies, if you send me R value references, rather than making copies from these guys, if you send me this, then I can actually take over this stuff. So there are in parameters that will be moved from, right? Think of it that way. So this is a simple example, guys, of how you might go about writing a copy, not a copy, a move constructor. Very simple and straightforward. All I'm doing is I want to take over this guy's stuff. Why? Because RHS has its pointer pointing to the heap memory, encapsulating a string, and the length data member contains some number. I want that stuff, and that is what I'm doing. And this is quite important. No except is a new keyword invented in 2011, which basically tells the compiler, and this no expect should show up both in the declaration and the definition. And actually, I could be wrong. Something at the back of my mind tells me that I should actually have put it here. Right between the semicolon and the closing parenthesis. So, but anyways, it's syntax, right? And the important thing is that you are promising to the compiler, hey, there's no exceptions that are going to be thrown. Remember, compilers are C C++ is designed to kind of make error detection and dealing with errors much more simpler than C. So exceptions are always at the back of in the runtime environment, and so it's quite important that you optimize as much as possible, and you're telling the compiler this guy can't ever throw any exceptions because it is not asking from anybody for to generate, to create new resources like file handles or memory or whatever. I'm simply taking stuff that already exists, right? So once you do that, notice to make sure that this guy is destructed properly, I assign the value null pointer to the pointer. This doesn't really matter. The important thing that you need to know is that this is all the standard requires. Later on, if you want, you can continue to extend the lifetime of this guy by assigning something to it. And that assignment operation will override the null pointer and the other stuff. Okay? So you got to make sure that both this guy and this guy are not pointing to the same memory. So think of it as a swap, but after the swap, we are making the R values point to null pointer. And this one, some people kind of write it like this. There are other ways to write it. The most common one is to check for self sort of, move. And just like we have self copy, well, we can have self move, but this one doesn't check for that. But we are simply swapping, right? And so swapping between the same thing, so nothing changes. And again, there is no except. That is quite important for speed up. It's one of the most critical tools in all your games. By default, every function should be no except. Then find a reason why it should not be no except. And hopefully with all the flags optimizations turned on, you'll get better performance. All right. The only thing left is to show you some code and also talk a little bit more. But I can complete that next class and move on to smart pointers. Are there any questions, guys? The best reference for all of this is the textbook. It contains very detailed discussion. Lipman is actually the guy who wrote the original C++ compiler with Strustrip, right? So he has a pretty deep understanding of the language, and the textbook is actually where I go many times. It is quite enlightening to read rather than, kind of looking for stuff. For me, the textbook is pretty good, especially with class design. And so I'm going to provide that as the reference. And next week we'll do some, or next class we'll do some code. Okay. So your vector class is going to have this constructor, and it's already built in. So it's going to take you a long time to build anything that is better than a vector or a deck. So if you use the vector, it obviously comes with all of the frills already built in. This guy is also built in. I build my own so that I can actually test them and see. So, but when it comes to production code, we have to use the standard library. I'll later on show you maybe once we're done with smart pointers about memory pools and that kind of stuff. It could be useful for your games, right? All right, so that is where we are, guys. Any questions? I think we covered pretty much everything that I wanted to, except the code part. So the critical part is this is going to speed up, and obviously less copies. And some of my example code will show you how the string class suddenly makes everything be better. Simpler logic and code. Yeah. So that leads us, since we have a couple more minutes, let me just talk about, you know, these are the now sort of like functions that can be synthesized by the compiler. Okay. Now, if you don't provide any copies, and then the compiler won't synthesize a move for you. It will generate a copy, but not a move. But if you provide a copy constructor, move constructor, then it'll synthesize the move assignment for you. So think of these 5, the bottom 5, okay, as some sort of a unit. If you have to write one, then probably you have to write all of the remaining ones, right? And that's what we call rule of 5. So we went from rule of 3 to rule of 5. And next class, we'll try to talk about rule of 0. If you declare any constructor, obviously we know this from HLP2, default is not generated. If you declare a copy operation but no move, then the move is not synthesized. How does the compiler know? Yes, we have the overloads now. One with the const reference and the other one with the R value reference. How does the compiler automatically do that? Well, in some cases, when we say return, right, the compiler knows. And it knows that we are returning by value. So it will find the best match. And that particular match in the modern language is R value reference if it exists. But you also saw that if there is no R values, okay, overloads, then you know now with all the stuff we did, oh my God. With all the things that we did, if you don't have an overload for this, well, it will choose the copy and it will do a copy. So that is the beauty of the copy constructor. It is catch-all. It's like a filter that can take everything. What we are saying now is in certain scenarios, I'm going to provide an overload of this that only works with this. Okay. All right, guys. I probably now can start. I do have the move to explain. I forgot. So I'll talk about it next class and then move on to smart pointers. Okie doke. All right.
Professor, can we have an ETA on when the next assignment or quiz will be?
Quiz. I want to have one every week. So there'll be one this week, and then I'll give out an assignment too. Right, this week. And one next week too on sort of move. And then the third one is to take a vector class and make it look more like the standard libraries. Because the one you guys built in HLP2, if you recall, it had the reserve and the capacity, but it couldn't separate construction and memory allocation and initialization. So I can explain that next class or next week, Tuesday, and then that gives you the ability now to adapt. If you have to write in an embedded environment, okay, or you're working in a place like Microsoft, whatever, then you do need these kinds of things. And if you know how to do these, then you can build your own classes. So I was thinking something like that would be the third. So the current next assignment, it has to deal with again binary files and function pointers and so on. I'm a kind of like I dropped the ball. I should have been a bit more sort of diligent in getting everything ready. But the problem is that in the classroom I can teach, using code and so on. Online I have to prepare these slides. Sure, they're good, but it gives everybody some sense of what was covered. But this one is taking up a bit of time because normally when I teach, I don't use slides. Okay, all right, I'll get going. No time to waste. All right, see you guys.
Thank you.
No problem.